Welcome back. In the last session, we are studying or we are understanding the amplitude distortion, the reason for amplitude distortion, right? What is the reason for amplitude distortion? The reason for amplitude distortion is non-linearity. If system is non-linear, we will get amplitude distortion which is not acceptable. That is not acceptable. Okay? Therefore, to get linearity from non-linear amplifier, we need to apply small signal. That is what I told, right? Even the system is non-linear, by applying small signal, we can get linearity in that portion. That is what is nothing but a small signal analysis. That's why the heading, if you see, BJT small signal AC analysis, MOSFET small signal AC analysis. The AC analysis, whatever you are doing, are the signals what you are applying at the input are small signals. You understand the point? That's why the name small signal, that is to get linearity. Okay? Therefore, this is what your DC equation maybe. Therefore, whatever VBE, right? VBU to IB relationship, right? What I told in the last class, this is non-linear. The relationship between VBE to IB is nothing but non-linear. That is the reason why non-linear amplifier, then we are getting it. Okay? I think you already taken the same thing. I can explain for the MOSFET also. Okay? Now, if you take MOSFET amplifier, let us take common source amplifier. This is RD and VDD, right? Drain, gate, source. Now, whatever input voltage are applying, that is VGS. That VGS is producing ID, right? For AC signals, it is small ID. Now, we want to know the relationship between ID to VI or ID to your VGS. If you consider DC equation, what is DC equation? ID is equal to mu n Cox W by 2L into VGS minus VT whole square. Level 1 or ideal model. Tell me what is the relation between VGS to ID. Therefore, your ID is function of or non-linearly, or I can say whatever VGS you are giving, which is what is producing ID. Therefore, this is non-linear. Therefore, the relationship between VGS to ID is non-linear. Then ID to V0 is linear, but what is input to output? Non-linear. Therefore, fundamentally your MOSFET amplifier is also non-linear. This is what is non-linear equation. This is what is non-linear equation. I already told you starting of the classes, the fundamentals. BJT, JFET, MOSFET, PN junction diode, right? All semiconductor devices with PN junction are non-linear with respect to voltage and current. Because they are non-linear with respect to voltage and current, ultimately we want linearity between input voltage to output current, output voltage. Because I am speaking about voltage amplifier, then indirectly the input voltage is converted into output current, but we know that is non-linear. Output current, output voltage linear, but output voltage to input voltage non-linear. Therefore, with respect to voltage amplification, they are non-linear. Whatever amplifiers we had studied till now, all are non-linear amplifiers. But remember, the non-linear amplifier is becoming linear amplifier by applying small signal. When you apply small signal, then the amplifier will become linear amplifier. I can explain mathematically also. When you apply small signal, that's what I told. Therefore, the non-linear amplifier, same thing. The non-linear amplifier is becoming linear amplifier by small signal input. By small signal input, it is becoming linear amplifier. It is becoming linear amplifier, right? This is what is becoming linear amplifier. If you ask me, non-linear means, let us say ID is equal to mu n Cox W by 2L into VGS minus VT whole square is becoming linear, means small ID is equal to GM into VGS. By applying small signal, then it is becoming what? ID is equal to GM into VGS. Therefore, remember, only for small signal inputs, only for amplifiers I am speaking. Even though fundamentally the DC signals are non-linear, doesn't matter. For biasing or keeping the transistor in saturation region and Q point stability, there we are not doing any DC signal amplification. We are only doing AC signal amplification, but that too, what signal you want to apply, that should be small signal. If you apply large signal to amplifier, you will get distortion, harmonic distortion. You understand the point? That is fine. Therefore, this is what is non-linear. Now, this is what is becoming linear. But we should know what is GM. That part I will derive. Okay? Mathematically also I can explain. Quantitative analysis. Quantitative analysis. If you take a quantitative analysis, right? Just listen. When I say the nonlinear system, let us say the nonlinear equation. If you consider nonlinear equation, let us say y is equal to ax plus bx square. This is what is nonlinear, right? This is what is becoming linear. This is what is becoming linear when axis tends to 0 or x is very small. It is not absolutely 0, x is very small. If x is very small, what about x square? X square is very small. I can say 0. Then y is equal to ax. Therefore y is equal to ax. I can say it is becoming very small linear, which is y is equal to ax provided x tends to 0. This is what is the condition which is what is required. This is nothing but small signal. I hope this is clear. But remember, yes, we are trying to convert non-linear amplifier into linear amplifier. I agree. But at what point and at what operating point you are operating the small signal, that matters. At what point you are operating the system, the non-linear portion, where it is becoming linear portion, the slope of the non-linear system gain is depending on operating point. That's why the gain is depending on GM. GM is depending on bias voltage. Therefore, it depends on operating point. Similarly, in the case of BJT, GM is depending on bias current IC by VT. Therefore, the system's AC gain is depending on DC bias points or DC operating point. Okay. What I mean is, mathematically I can explain. Therefore, this is what your VI and this is what your V0. Practically non-linear. Then where are you operating? Let us say if I operate here, this is what is my operating point, right? Then if I operate here, then let us say this is what is my small signal analysis. Then this is what is my small signal analysis. If I do, let us say, then this is nothing but what? This is what is having slope. Now, if I take, let us say this is what is my operating point now. For the same input, now if you ask me the output, right? The output is very small. What else may be? Now this is what is our linearity you are getting. Therefore, this is what is operating point. Now this is what is having the slope. Let us say this is what is my operating point, having the slope, the tangent. Here the tangent is this. Therefore, the slope is different with respect to operating point. This is what is Q1, this is what is Q2. The slope of the system, the slope of the system is depending on operating point. It is depending on Q point. The slope is nothing but what? Gain of the system. Therefore, the gain of the system is function of, the gain is function of operating point. Therefore, V0 by Vi is nothing but your gain, right? The output peak to peak divided by input peak to peak is nothing but your gain. Therefore, let us say I am operating here. That is what is my operating point. Then output peak to peak divided by input peak to peak. And we are applying small signal input. Therefore, we are getting linear or without any amplitude distortion output. Now, when I say this is what is my operating point, but I am giving the same small signal, but I am not getting the same output. Why? Because the operating point is different, the slope is different, the gain is different. Therefore, the gain, AC parameter, gain is AC parameter, is depending on the operating point. Therefore, DC bias voltage. That's why in the case of BJT, if you take your voltage gain, right, we got minus GM into, if I take BJT amplifier, minus GM into the load, where GM is nothing but, IC by VT. That's what I used to say, right? IC by VT, where IC is nothing but DC bias current. Therefore, the voltage gain is function of operating point. IC is depending on operating point, right? What is operating point? VCE comma IC. Therefore, IC is nothing but your operating point. Similarly, we need to know what is GM of your MOSFET. Then your MOSFET or FET amplifiers are also over. Only the topic which is left from FET amplifiers is to derive the GM of your MOSFET. I already derived what is GM in the case of BJT from hybrid 5 model, right? Then we got IC by VT. Similarly, what is GM of MOSFET? The formula based on the definition. Hope this is over. Now we can go to the last topic under FET amplifiers, the transconductance GM. Over. 10 more seconds. The graph is important to understand, okay? Without graph, whatever equations, whatever sentence format we explain, difficult to understand. Actually, the graphs, signals, these are all easy to understand. That's why people go with timing diagrams and all to explain few concepts, okay? That's fine. Now, GM of your MOSFET. Therefore, if you consider your MOSFET, drain, source, gate. Okay, now this is nothing but your VGS, and this is your ID, and this is your VDS. That's it. We don't have gate current, no need to represent that. Okay, GM of transistor is defined as, just take the definition. The definition is, GM is defined as the change in ID, because of change in VGS only. The change in output current only because of input voltage, not because of anything else. That is what your GM. To make that, keep VDS constant. Keep VDS constant. Because we are looking for not ID by VGS. Remember, it's not ID by VGS. It is change in ID because of change in VGS. Then if you keep VDS constant, then the change in ID because of VDS, because VDS is not changing. Then ID change because of VDS is not there. Then ID change because of VGS is there. That is what is your GM. What is the change in ID because of VGS? That is what is your transconductance. Therefore, VDS is constant, or delta VDS is equal to 0, or small VDS is equal to 0. Okay. Now, if you know this definition, then we can go ahead, right? And we know that if you take linear equation, ID is equal to, DC equation, mu n Cox W by 2L. I already explained what is mu, what is Cx, what is W by 2L and all, right? VGS minus VT. If you forget, go back to the starting of the classes. Okay, then refer. Therefore, ID is equal to mu n Cox W by 2L into VGS minus VT whole square, which is level 1 equation without channel length modulation. If you consider channel length modulation, you'll get 1 plus lambda into VDS. I'm not taking channel length modulation. This is what is your ideal model. Now differentiate this ID with respect to VGS, then you'll get GM, right? Right? Therefore, number 1. Okay, I'll tell you. Therefore, what is GM? Therefore, if you differentiate, you will get mu n Cox into W by 2L into 2 into VGS minus VT. 2 will be cancelled. Therefore, it is simply mu n Cox W by L into VGS minus VT. This is what is our GM. This is what is first form. Therefore, this is what is first form or equation 1. Therefore, this is GM. Now, if you ask me what is the GM with respect to VGS minus VT or VGS, okay, this is what your GM, then tell me, can I say this is linear? Because Y is equal to mx plus c, whatever may be. Therefore, Y is equal to, if VGS is increasing, your GM will increase. Therefore, the AC parameter GM is depending on the DC input operating voltage. That is what I want to say. I already told, right? Therefore, GM is function of VGS. Therefore, this is function of VGS. Capital VGS is DC parameter, but GM is AC parameter. Therefore, your GM is small AC parameter and VGS is DC parameter or DC bias voltage. DC bias voltage. Okay, just listen, don't write. Now, second form of GM. Second form of GM. This is also GM, but second form of GM. You can call this as equation star. Okay, that is fine. Therefore, we know that we already got, right? What is GM? We know that GM is equal to mu n Cox W by 2L into VGS minus VT whole square. VGS minus VT. That is what is your GM. I want to write in terms of VGS. I want to write in terms of ID. Okay. Can I convert into ID? Yes. What is VGS minus VT whole square? Star implies VGS minus VT whole square is equal to 2 into ID divided by mu n Cox W by L. Don't separate W by L because W by L is strength of the MOSFET. Okay, don't take it L by W. Okay, keep it like W by always. Then if you take out the square, this is what is becoming square root. Right? Then now what is GM? You substitute this. Therefore, GM is equal to mu n Cox W by L into what is VGS minus VT? 2 into ID divided by mu n Cox W by L. Therefore, mu n Cox W by L, mu n Cox W by L. If you take this inside, square, and then this will be cancelled, then you will get mu n Cox or 2 into ID. Already we have 2 into ID into mu n Cox W by L square root. Therefore, this is what is our GM. This is second form. But here it is function of what? It is function of ID. This is function of ID. If you ask me GM to ID relationship, this is your ID and this is what is your GM. Then y is equal to root x. Then x is equal to y square. Then what kind of this? Then you will get GM like this, which is non-linear. What it may be? The relationship between AC parameter to DC operating voltage or operating current is non-linear. What it may be? It is depending on ID. Mathematically all are same, but qualitatively all are not same. What it may be? Now we have another form. Don't write. We have the last form. Third one, GM, right? I want to write in terms of both VGS and then ID. Can I write? Let's see. We know that what is GM? GM is equal to mu n Cox W by L into VGS minus VT, right? And what is ID? Star implies what is ID? ID is equal to, can I write it like this? Mu n Cox W by L into VGS minus VT into VGS minus VT by 2. Can I write like this? By 2 VGS square. Then what is this? This is nothing but GM, right? Therefore, GM is equal to 2 into ID divided by VGS minus VT. This is another form. This is what is our GM. This is third form. But if you ask me, I want to draw with respect to VGS when ID is constant. When ID is constant, you will understand the meaning of all these things. When ID is constant, then I want to know GM with respect to VGS. Then it is nothing but what? Y, X. XY is equal to constant. Rectangular hyperbola. You will get like this. But just take mathematically, but the qualitative meaning of this I will explain. Here it is function of both VGS comma ID. It is function of both VGS comma ID. Therefore, when ID is constant, let us say, then what is GM with respect to VGS? That is what is your GM. And if you ask me, right, just don't write. If you ask me, people call this as GM is only function of VGS. If you write like that, this is what is voltage bias. This is what is voltage bias. We are biasing with input voltage. But these circuits we did not see actually. Mathematically it is nothing but writing GM in terms of ID and then writing GM in terms of ID and then VGS. That is fine. Mathematically, yeah, these are all straightforward. But qualitatively they are not same whatever we had seen. Like common source amplifier with passive load, passive RD. Then instead of RD, if you put a current source where output current is constant, then these two will come into picture. Okay. If time permits, I will try to explain. This is what is current bias. Because your output current is biasing your transistor, not input voltage. Whatever output current you are pumping to current source, right? That is what is biased using. That is nothing but CMOS amplifier. That is fine. Current bias. And here actually both are same, but output current is constant, But input voltage, input bias voltage, if that is changing, then there is a fighting between ID to VGS through the transistor. Then there is something called W by L of the transistor to be adjusted such that VGS is changing but ID is constant, right? Then we have to adjust W by L such that both will be equal. Then that is what is called technology bias. I'm just giving you the terminology, but even though you don't know what is the qualitative part of these two, not required for our syllabus, GATE examination, therefore this is what we are using, this is what is enough, okay? Take it. Three forms of GM, okay? Just treat like mathematical equations, the qualitative part of this you will get when you enter into higher education, okay? Because it is scope of our syllabus, CMOS amplifiers and all, therefore only we have just common source amplifier and all, therefore where we use RD as the bias resistor, right, passive resistor, then that is what is your voltage bias. Input voltage R1, R2, whatever we have from self bias circuit, that is what is biasing your transistor, okay? That's why this is called voltage bias. Maybe little bit I'll explain difference between voltage bias to current bias. Remember, practically people go ahead with the current bias, but whatever we have in our syllabus using voltage bias, okay? Means whatever amplifiers we had seen till now, common source amplifier, CS with RS amplifier, CD amplifier, CD with RD amplifier, CG amplifier, all are current voltage biases. We didn't apply current bias. I'll explain what is current bias, what is the difference between voltage bias and current bias. And both are same only, but because when I say current bias, ID will be constant. When ID is constant, let us say if input VGS is changing due to some reason, then how will you get GM? That is what is, by adjusting W by L. I told you already, then we will get it. So do not see any discrepancy or fighting between input to output of transistors. Okay, that's fine. I'll give you 3 minutes to write. 1 minute, 1 minute, 1 minute. With this I can say MOSFET is over. FET amplifiers are over. We have to solve classroom workbook problems. Okay. See, you have one more student workbook, right? That you try at your home. Okay. Without seeing the solutions, then you try at your home. Then if you don't get it, then go for the solutions part, which we see. Okay. Done. Last 30 seconds. Then I'll explain the difference between voltage bias and current bias. I'll stop this session. Okay. Sufficient time is given, therefore I hope this is clear. Done? Okay. I'll explain the difference between voltage bias and current bias. Then I can say this is done. Just don't write anything. If you take common source amplifier, this is what is voltage bias, okay? VI and V0, RD, VDD. Tell me what is voltage gain? Minus GM into RD dash, right? Therefore, what is RD dash? Minus GM into RD in parallel to small RD. For example, for your understanding, let us consider channel length modulation is equal to 0. Let us say lambda is equal to 0. Then what is your voltage gain? Means, excuse me, your small RD is infinity. Okay, then what is your voltage gain? Minus GM into RD. That is fine. Therefore, this is what is voltage bias. Because your GM is set by voltage. Then if you ask me what is GM, then GM is equal to mu n Cox W by L into VGS minus VT. In the case of BJT, what is GM? IC by VT. Okay. Now, therefore, this is what. But I want to increase the voltage gain. I am thinking from improvement. If I want to increase my voltage gain, just mathematically, tell me, if I increase my RD, can I increase my voltage gain? Yes. But remember, if you think from AC perspective, if you increase RD, whatever you want, then whatever drop or whatever VDS you are getting, that VDS will be decreasing, then it may enter into linear region, then it will not act as an amplifier. It will not act as an amplifier. Therefore, the transistor may come out of saturation region and it will be entering into linear region, then we will not get amplification, because we want VDS should be greater than or equal to VGS minus VT. VGS means the bias voltage. If that VDS is coming less than that, then it will be entering into linear region. Therefore, we cannot increase RD whatever you want. Mathematically from AC analysis, I am saying that yes, right, we can increase and then we can improve the voltage gain, but it has some limitation. Now what I do, I want to have RD infinity, then I'll get voltage gain very high, R infinity, right? But I want to have some path. That is nothing but what? That is nothing but your CS amplifier, but with active load. This is what is called with active load. Active load. This is what is called passive load. This is passive, right? This is passive load. And what does it mean? It is now biased with a current source. Let us say this is what is your I bias. This is your bias. Then this is your VI, right? Now this is what your V0. Then tell me now, your circuit is biased. If you ask me what is current source internal resistance, infinity. Then if you ask me what is your voltage gain, your voltage gain is equal to minus GM into RD dash. What is RD dash? Minus GM into RD in parallel to small RD. But what is small RD? Small RD is infinity. Therefore, you will get just into small RD. If channel length modulation is not there, then your voltage gain is becoming infinity. This is ideal scenario. But practically, this is what is defined with small RD, intrinsic gain. That's why you remember I told, right? GM into RD is nothing but amplification factor. That is the intrinsic gain we get from your transistor, provided that is what is having the current source. Now, if you ask me, if the difference between this is what is your, remember this is what is current bias. Because you are biasing the transistor with respect to I bias. This is what is called current bias. Where in this case, what is GM? GM is equal to mu n Cox W by L into, which is nothing but 2 into ID mu n Cox W by L. This is what is your GM. Okay? Because that is what is your current source. Therefore, current bias. Therefore, you are getting maximum voltage gain. But how to get this current source and all? Again, this itself is extra. but I'm explaining. Therefore, how to get this current source and all, I'm not explaining, but let us see if you have a current source where output current is constant, then your GM is defined with the output current. ID is nothing but I bias. Then you'll get GM. If you know GM, your voltage gain is minus GM into small RD. If you neglect channel length modulation, your voltage gain is infinity ideally. But practically channel length modulation is there. Therefore, practically it is defined with minus GM into RD. Hope this is what is clear. Therefore, this is what is voltage bias. Because your GM is defined with capital VGS, this is not shown. Actually, R1, R2. Okay, that is what. Similarly here, then what does it mean? Let us say R1, R2, I am giving different VGS. Then different, but this is fixed with current source. Then if you change your VGS, that's what I told, that is nothing but technology bias. We have to adjust W by L of the transistor such that whatever VGS you have from the DC voltage, then the I bias whatever you have, both should be matched. Therefore, current bias or technology bias, both are almost same. Both are having active loads. Okay, this is what people practically use. Practically people use this. Earlier people used to this, but nowadays people are using this. Okay, take it. I'll stop the session. With this I can say FET amplifiers are over. Okay. Because the current source internal resistance is infinity. Ideal current source internal resistance is infinity. Therefore, your capital RD is nothing but infinity. But still there is a current which is what is sourced by your current source. We didn't see these circuits. We have seen with respect to RD, RS, etc. Okay? With passive loads. Only with active element which is your MOSFET. You can continue, right? I'll stop now.